Okay, so we are talking about the context free language for which we have corresponding a context free grammar G, which is VTPS, such that it is accepting the it is generating the language. So, if L is a CFL context free language, then we called L to be CFL. L is coming from sigma star, which is nothing but T star. T is sigma over here. T is the set of input alphabet, or in the grammar sense we call T is the terminals. So, it is a collection of string of terminals or string of input alphabet, we can say in the terms of the automata. So, okay, so when we say this is a CFL context free language, if we have a G grammar which is generating this language, then we call this is a context free language, if such a grammar exists. And we have seen for every context free grammar we have it will correspond there we have a corresponding PDA, push down automata. So, push down automata is to accept the which is called context free language. So, for this we have a PDA M which accept this, that means the language of this language. There are two ways of we can define the language accepted by a PDA, either in terms of the final state or in terms of the empty stack. So, this will be L. Okay. Now, then we have this is a context free language. Now, we will discuss what is the what is the difference or what is the relationship between the regular language and the context free language. Okay, so, let us take a language which is regular. Let L be a regular language. Over a input alphabet sigma, or we can refer this to be a T. T is the set of terminals, but we usually use the sigma for the automata when we discuss the automata. So, this is regular means what? Regular means there is just a finite automata. It could be DFA, it could be NFA, it could be epsilon NFA, all are equivalent. So, we can take any finite automata M, which is Q sigma delta Q0 F, such that it is accepting the language, such that L is nothing but the language of that finite automata. Then we call this is a basically a regular language. Any language is called regular if we have a corresponding finite automata whose language is the language of that L. Okay. Now, we know the finite automata can be, for example, DFA, it can be viewed as a PDA, push down automata. Why? So, this can be viewed as a can be viewed as a PDA, push down automata, in the sense of anyway both are same accepted by the final state, because in push down automata what we have the all are same Q, and we have a stack symbol over here, and we have delta, then Z0, Q0 and F. Now, everything is same except we have a new concept which is called stack symbol, but that we can anyway this is we can ignore, we can put anything in the stack. So, make sure that stack will be never be empty through that way. So, we can keep on putting something on the stack in each step. So, that way, because we are accepting in that sense of final state. So, that way we do not care about stack, but only thing we have to be careful, when the stack got empty, then there is no move, our automata stuck, our PDA stuck. So, that we have to be careful on that. So, given a finite automata, we can view it as a push down or PDA. So, that means what? That means this is a regular language is and push down automata means it is corresponding to a grammar. This will corresponding to a grammar G, which is V sigma and then P and S, which will sigma is this same sigma and which will generate the same language. So, basically the regular language is a context free language. So, every regular language is a context free language, because it is a finite automata which is accepting that and it will give us the. So, every regular language is a. So, every regular language is a context free language. Okay, because it is nothing but a push down automata which is accepting that, and push down automata is nothing but a context free grammar and so on, hence that is a regular. So, if we see this R is a set of all regular language. So, if we denote this R is a set of all regular language over sigma, and C, or we denote this L, anyway this is just a symbol. L is the set of all CFL context free language over sigma. So, that means this any regular language is a context free language. So, R is a subset of this L. Now, the question is the other one is true. So, R is a subset of L. Okay. Now, the question is the reverse. I mean, is the every context free language CFL is a regular? So, is every CFL is, we know this answer, regular. So, what is the answer of this? We know this answer. So, the answer is no. So, then we have to take a counter example which is CFL, but it is not regular. So, who can remember this? So, we know this 0 to the power n, 1 to the power n is greater than or equal to 1, this language. If we consider this language, this is a CFL. Why? Because we can construct a grammar G V 0 1, this is our sigma or T, and P S. So, V is only S, say, only one symbol. So, what are the rules? Rules are basically S is going to 0 S 0 or 1 S 1 or epsilon. So, if you take that grammar, it will generate the all the string like this. So, this grammar will generate the L. So, that means this is a CFL context free language, but is this the regular language? We know this. No, this is not a regular language. Why? Because it is not satisfying the pumping lemma. Pumping lemma is a necessary condition to be a language to be regular. So, this is not satisfying the pumping lemma. So, this is not regular. We can say by using pumping lemma, we can by using pumping lemma. Okay. So, this is not regular. So, now the question is, so this is not a subset, then the picture is like this. We have a set of all regular languages, say this is set of all regular languages. Okay. And then we have other set which is CFL. So, because regular language is a CFL, every regular language is a context free language, but not every context free language is regular. For example, we have some member over here like 0 to the power n, 1 to the power n. There are many examples of the language which are context free language, but which are non regular. Using pumping lemma, we can show that. Okay. So, now we will talk about some closure properties of the CFL. Closure properties of CFL. We know the closure property of a regular language, that means, if we have two language L1 and L2. So, given a input alphabet, it could be 0 1, it could be AB, it could be anything. So, it is a finite set of symbols, input symbols. So, given this input symbol, if we take two language L1 and L2, which is subset of sigma star, then if these both are CFL, let this be CFLs, two context free language, then we can show these are the properties, like it is closure under union, then L1 union L2 is CFL, and it is closure under concatenation, L1 L2 is CFL, and it is closure and under clinic closure like this L star, L1 star is a CFL. Okay. So, we will slowly check these properties of the regular context free language. So, first we will check the how this is closure under union. So, suppose we have two language which is regular, which is CFL. L1 is CFL means what? Means we have a context free grammar which is generating this. So, that means, we have a grammar G1 which is V1 sigma, we can take same, I mean it is T1 basically, T1 and T2 for the other, but we can without any loss of generality we can take the same sigma, or we can take union of that for, but anyway does not matter. So, then P1 and then S1 such that L of G1 is L1. This is the first CFL which is corresponding gamma is G1, and since L2 is also a CFL, we have corresponding, we should have a grammar G2 which is V2, we can take the same input, but again I am telling we can take T1 T2, then we can take the union of that, but that is okay because we are talking about the language over a set, input set. So, P2 and S2 such that S2 is the starting variable of the second grammar, such that L of G2 is L2. The language generated by this gamma G2 is nothing but L2. So, this is the situation. Now, we want to show that L1 L2 is a CFL, L1 union L2 is CFL. So, for that what we need to do? We need to construct a grammar from these two grammar such that these two are, I mean that will accept that will generate the L1 union L2. So, what is L1 union L2? L1 union L2 is the set of all strings such that W is either in L1 or W in L2. That is the union definition we know. So, now the question is how we can construct a grammar L which will generate this. So, this is not tough to construct. Okay, so, we will try to construct a G. We take help of say V is a variable set, sigma we take same, otherwise we have to take T1 union T2 if we take the different terminals. But we are talking about over the same input alphabet, so we are taking sigma over here. and then we take a p we have to define, and we take new starting variable S3. Okay. Now, what is V? V is V1 union V2 union S3, and here without loss of generative we can assume that there is no common variable in V1 V2, because if there is common name we can always rename that, there is no harm of renaming the variable. So, this is okay, this assumption is okay, that V1 V2 are not containing, I mean their intersection is null, I mean they are not containing any common variables. Okay. Now, how to define the rules for P? So, P rules for P will be P1, we will keep the rules for G1, rules for G2, and we add a extra rule which is to accept that union. So, which is basically we starting with S3, it is going to either S1 or S2, that is all. So, this will make us, I mean this is the rule whether we are going for, I mean we are taking all the rules from all the transition of all the productions of G1 and G2, that is P1 P2, and apart from that we are taking two extra production, that S is going to S3, the starting variable of the new grammar is going to S1 or and S3 going to S2, and S1 S2 are nothing but the starting variable of this. So, this will make us acceptance of L1 union L2. So, how? So, we will check that how this can be, this can accept a. So, if we take a W, so what is L of G then? Our claim is L of G is L1 union L2. Okay. Now, if we take a W which is L1 union L2, that means this implies W is either belongs to L1 or W belongs to L2. If W belongs to L1, so what we do? We first take this move, S3 is going to S1, and then as W belongs to L1, then we know this is going to W. So, that means because this is the accepted string of G1, so that means we have a derivation, either leftmost derivation or parts tree anyway, but we have a derivation from H1 to that string W. So, that means eventually we have a derivation from S3 to W in G. So, this is in G1, because G1 the production of G consists of production of G1 and production of G2. So, like this. So, similarly we can show that other way, that if a string is accepted by a L of G, so it has to be accepted by either a L1, if it has to be in L1 or L2. So, that means L of G is nothing but, okay. So, this is the construction, very simple. Now, how to construct the concatenation? Like we know if L1, so L1 is a context free language. So, we have a G1, V1 sigma we are keeping same over here, P1 S1, and L2 is another context free language. So, we have corresponding this thing, corresponding grammar, context free grammar, which is generating this. Here we could take T1 T2, then we have to take their union, but since they are coming from sigma, we can take sigma for simplicity, there is no harm with that, because sigma we can consider the T1 union T2. Okay. So, that is fine. Okay. So, now L1 concatenation L2 means this is set of all strings. So, this is L, all string of the like form like x y such that x is coming from L1 and y is coming from L2. Okay, x is coming from L1 and y is coming from L2. Now, the question is this regular, is this CFL? So, answer is yes, but for that we need to construct a G context field grammar which can generate this. So, how to get a G? Yes. So, let us construct a G which is V set of variables, sigma will be same and P, and now some new starting variable S3. Okay. Or we can say S. Anyway, we have used S3, this is or S. Okay. Okay. So, now what is V? V is nothing but set of all variables of G1, set of all variables of G2 and the new starting variable S. Now, what are the rules? Rules are basically rules of P1, rules of P2, this is the productions, and we are introducing new rules where, because we have to accept y x like this. So, that will be like this, S is going to S1 S2, that is all. This is the concatenation. I mean, this is the new rule we are adding. So, we have the productions of P1, we have the productions of P2, and then we are introducing the extra rule the production that S is going to S1 S2. So, that will give us the concatenation will be accepted. So, we can show that L of G is nothing but L1 L2. How? Because if we take this if we take any W belongs to L1 L2, that means W will be of this form x y. Now, x y are all coming from and x is belongs to L1 and y is belongs to L2. Now, to accept x we need to, so we can start with this S1 S2. Now, we can have a derivation for S1 and it will eventually lead us to, so this is for G1, eventually lead us to x S2, because x is a terminal strings which is generated by this G1, and then again y is a terminal string which is generated by G2. So, this is G2, this will eventually lead us to y. That means, this S will be x y. Okay. So, this extra rules will give us this production. So, that means, this will give us L1 and L2, the G of L of G is nothing but L1 concatenation L2. This is the concatenation. Now, the question is the union. Is the CFL is closed under union? Sorry, intersection. Union we have seen, closed under intersection. Okay. That means, if we have given two L1 and L2, again I am telling this could be from the different sigma, different T1 T2, but we can take the union of T1 T2 as a sigma. So, there is no harm by taking L1 is coming from sigma and star. So, we can take one input alphabet, there is no harm. So, these are all these be CFLs. Now, the question is whether L1 intersection L2 is a CFL or not. We know these properties for the regular language, right. If I have two language which is regular, their intersection may not be regular. So, same thing is followed by here. I mean this intersection not always will be regular. So, this we can so this is answer is no, not always. So, if we have two regular language, if we have two context free language which are I mean then their intersection need not be a context free always. So, to show that we need to take help of a counter example. So, for that we will show L1 will take two regular language context free language L1 and L2 and we will show their intersection is not regular. Intersection is not CFL. So, for that we will take some counter example. For that we will use what is called pumping lemma. Pumping lemma for CFL, which is necessary conditions for a language to be a context free language. Then using that pumping lemma we will show this is not regular. So, that we will discuss in the next class. Thank you.